Shape memory polymers, design principles, stimulus responsiveness, and applications. Shape memory elastomers, SMEs, are an emerging class of smart polymeric materials capable of recovering a predetermined permanent shape after deformation when exposed to external stimuli such as heat, light, electricity, magnetic fields, or solvents. By combining the elastic characteristics of elastomers with the shape memory effect, SME, these materials exhibit large reversible deformation, rapid recovery, and excellent fatigue resistance. Their unique properties make them attractive for applications in biomedical devices, artificial muscles, actuators, soft robotics, flexible electronics, and aerospace systems. This report summarizes the mechanisms, molecular design strategies, stimulus response mechanisms, and practical applications of shape memory elastomers, highlighting recent developments and representative material systems. Shape memory materials are capable of recovering a predefined permanent shape from a temporary deformed configuration when stimulated by external triggers. This phenomenon, known as the shape memory effect, SME, was first observed in metallic alloys in the early 20th century and has since been widely studied in alloys, ceramics, polymers, and composite materials. Elastomers represent a special class of polymers characterized by rubber-like elasticity and viscoelastic behavior. According to the ASTM definition, elastomers are natural or synthetic polymeric materials capable of undergoing large reversible deformations and returning rapidly to their original shape once the external stress is removed. Their low glass transition temperature, TG, flexibility, and high extensibility provide advantageous properties such as chemical resistance, durability, excellent adhesion, and good electrical insulation. The integration of the shape memory effect into elastomeric networks produces shape memory elastomers, which combine the flexibility and elasticity of elastomers with programmable shape recovery. Compared with traditional shape memory alloys or ceramics, SMEs generally exhibit lower density, higher deformability, improved cyclic stability, and easier processing. Consequently, they are increasingly explored for applications in soft robotics, intelligent textiles, biomedical devices, aerospace structures, and emerging technologies such as 4D printing, where objects change shape over time in response to environmental stimuli. Molecular design and mechanisms of shape memory elastomers. Fundamental shape memory mechanism. The shape memory behavior of elastomeric polymers arises from their molecular architecture and thermodynamic behavior. Key factors governing the shape memory response include molecular structure and chain orientation, crystallinity and phase morphology, cross-linking density, intermolecular interactions, programming conditions. The programming process typically involves mechanical deformation at elevated temperature. The polymer is first heated above its transition temperature, either TG or melting temperature, trademark, allowing polymer chains to become mobile. Mechanical deformation is then applied to produce a temporary shape. Subsequent cooling below the switching temperature, Ts approximately equals TG or trademark, immobilize the molecular chains, fixing the temporary configuration. When the material is reheated or exposed to another appropriate stimulus, molecular mobility is restored. The stored elastic energy within the network drives the polymer chains back to their lowest energy configuration, thereby restoring the original shape. Structural elements of shape memory elastomers. The molecular structure of shape memory elastomers typically contains two functional components. Net points, fixing phase. These are permanent cross-linked networks responsible for defining and stabilizing the permanent shape. Net points may arise from covalent cross-links, crystalline domains, or strong physical interactions. Switching segments, reversible phase. These segments undergo reversible phase transitions such as glass transitions or melting. They allow the temporary shape to be fixed and subsequently released when stimulated. Effective SME design requires that these two phases possess distinct transition temperatures and maintain good compatibility within the polymer matrix. The actuation performance can be optimized by controlling chain orientation, crystallinity, and the balance between amorphous and crystalline domains. Examples of common shape memory elastomer systems include polyurethane-based elastomers, silicone elastomers, e.g., PDMS networks, thermoplastic polyurethane, TPU, polycaprolactone, PCL, elastomer networks. Shape memory performance and classification. Dual, triple, and multiple shape memory effects. Shape memory elastomers can be classified according to the number of temporary shapes they can store. Dual shape memory effect, DSME, the polymer remembers one permanent shape and one temporary shape. This is the most common SME. Triple shape memory effect, TSME. The material can store two temporary shapes before returning to its original configuration. Multiple shape memory effect, MSME. More complex systems can memorize three or more temporary shapes by incorporating multiple reversible phases with distinct transition temperatures. Achieving multiple SME behaviors requires precise molecular design because each additional reversible phase introduces extra phase transitions and reduces the proportion of each switching segment. One-way and two-way shape memory effects. SMEs are also categorized based on reversibility. One-way SME, 1W-SME, the material recovers its original shape when stimulated, but requires external programming to reintroduce the temporary shape. Two-way SME, 2W-SME, the polymer can reversibly switch between two shapes upon cyclic stimulation without external reprogramming. Two-way behavior is more challenging to achieve and often requires specialized crystalline or liquid crystalline polymer networks. Stimulus-responsive shape memory elastomers. Thermoresponsive shape memory elastomers. Thermally activated SMEs are the most widely studied systems because temperature can easily trigger phase transitions. When heated above TG or trademark, the switching segments become mobile, enabling recovery of the original shape. Typical thermoresponsive systems include polyurethane polycaprolactone elastomers, cross-linked polycaprolactone networks, silicone elastomers with crystalline switching domains. For example, cross-linked PCl-based elastomers with melting temperatures near 45 to 60 degrees Celsius can be programmed into temporary shapes and recover their original structure upon heating. Light-responsive shape memory elastomers. Light-responsive systems offer improved spatial and temporal control over actuation. These materials typically rely on photothermal conversion, where absorbed light is converted into heat to activate the SME. Photothermal agents frequently incorporated into elastomer matrices include carbon nanotubes, graphene gold nanoparticles, carbon black. Near-infrared, NIR, radiation is commonly used because it penetrates materials and biological tissues efficiently. NIR-triggered SME systems have been demonstrated in biomedical implants and remote-controlled soft robotic devices. Electro-responsive shape memory elastomers. Electrically responsive SMEs rely on conductive fillers to generate dual heating when voltage is applied. This heating raises the material above its transition temperature, triggering shape recovery. Common conductive additives include carbon nanotubes, CNTs, graphene oxide, carbon black metallic nanowires. For example, a composite of thermoplastic polyurethane, TPU, polylactide, PLA, and multi-walled carbon nanotubes, MWCNTs, can achieve rapid electrical actuation with recovery efficiencies approaching 90% under moderate voltages. Magneto-responsive shape memory elastomers. Magnetically responsive SMEs contain magnetic nanoparticles that generate heat when subjected to alternating magnetic fields. This heating activates the switching segments and triggers shape recovery. Typical magnetic fillers include magnetite nanoparticles, magamite nanoparticles. These systems are promising for wireless actuation, particularly in biomedical applications where direct heating or electrical stimulation may be impractical. Solvent-responsive shape memory elastomers. Solvent-responsive SMEs rely on swelling or plasticization effects induced by solvent molecules such as water. Solvent uptake increases chain mobility and lowers the effective transition temperature, enabling shape recovery. Such systems are attractive for biomedical applications because water is biocompatible and naturally present in biological environments. Multi-responsive shape memory elastomers. Multi-responsive SMEs combine several activation mechanisms within a single material system. These materials can respond to combinations of stimuli such as heat and light, heat and magnetic fields, electricity and light, humidity and temperature. Such systems expand the functional range of smart materials and enable advanced applications in adaptive structures and programmable materials. Applications of shape memory elastomers. Biomedical devices. Shape memory elastomers are particularly attractive for biomedical engineering because of their flexibility and biocompatibility. Applications include self-expanding vascular stents, minimally invasive surgical tools, drug delivery systems, artificial muscles and tissue scaffolds. For instance, biodegradable PCl-based SMEs have been explored for implantable devices that expand to functional shapes once inside the body. Soft robotics and actuators. SMEs are widely studied for soft robotic systems that require lightweight and flexible actuators. Their large deformation capability and high recovery force make them suitable for soft robotic grippers, artificial muscles, adaptive robotic components. Silicone-based SMEs reinforced with carbon nanotubes have been used to create remotely actuated robotic devices. Aerospace and deployable structures. In aerospace engineering, shape memory elastomers enable lightweight deployable structures such as self-deploying antennas, morphing aerodynamic surfaces, compact satellite components. These systems can be launched in compact shapes and activated to deploy once in orbit. Smart textiles and wearable devices. SMEs are increasingly integrated into adaptive textiles capable of responding to temperature or humidity changes. Applications include self-adjusting garments, wearable sensors, responsive protective clothing, 4D printing and programmable materials. One of the most exciting developments is the use of shape memory elastomers in 4D printing, where printed objects change shape over time in response to environmental stimuli. Such materials enable programmable structures capable of dynamic transformation. Challenges and future perspectives. Despite their significant potential, several challenges remain in the development of shape memory polymers. These include improving mechanical strength, enhancing recovery efficiency, achieving precise stimulus control, and developing scalable manufacturing techniques. Furthermore, complex SME behaviors such as multi-responsive and two-way shape memory effects require a deeper understanding of polymer network architecture and molecular dynamics. Future research is expected to focus on advanced molecular design strategies, nanocomposite reinforcement, and integration with emerging technologies such as flexible electronics, biomedical implants, and adaptive robotics. Conclusion. Shape memory polymers represent a rapidly evolving class of smart polymer materials that combine large elastic deformation with programmable shape recovery. Their unique molecular architecture, consisting of permanent cross-link networks and reversible switching segments, enables controlled transformation under various stimuli, including heat, light, electricity, magnetic fields, and solvents. Because of their flexibility, durability, and responsiveness, SMEs are expected to play a crucial role in next-generation technologies ranging from biomedical devices and soft robotics to aerospace structures and intelligent textiles. Continued advances in polymer chemistry and materials engineering will further expand the capabilities and applications of these versatile smart materials.